Hello.
Good morning. Good morning, everyone. Hi, nice that many of you could join us on this third webinar for the FABULOS Academy. Oscar Nissin, we have here, our presenter of today. My name is Renske Martijnse. I'm the FABULOS Project Coordinator from Forum Virim Helsinki. You can find a bit more information on the project via the website, fabulos.eu. I think that for now, I will just very shortly say that this project revolves around autonomous mobility, so self-driving buses, to be exact, for public transport. So these type of robot buses, they are the topic of today as well. In FABULOS, we have 6 cities or 6 procuring authorities involved in our project, and another 20 or so follower authorities who are also very interested in possibly procuring this kind of system that can operate fleets of robot buses in cities. And all these authorities, cities or ministries or public transport authorities, they have to increasingly deal with this automation in public transport, and they don't always have the knowledge that they might need for this when they have to deal with tender documents, for example, and tendering. So even though you don't need to know all the details, it's very good to have a basic knowledge of how these systems work, and that's why we put up this FABULOS Academy. So it's a series of 6 webinars about technical aspects of robot buses. So we've already discussed electrical properties and charging aspects, and also also some legal aspects we've discussed. And today it's about sensors mostly, and really diving into the technical things. There are still 3 webinars to go after the summer. The 4th webinar will be on the 3rd of September on cyber threats and threat mitigation, so cybersecurity. So I warmly invite you to also register for that. So everyone's welcome. This is, of course, an open webinar, not only for procuring authorities, for everyone who's interested. And we're happy today to have Oscar Nissin as our presenter. Oscar works for Metropolia University of Applied Science here in Helsinki in Finland, and he has a really broad experience in this field and has been involved in the robot buses ever since, from the start. Yeah. Oscar is also the technical partner in the FABULOS project, and he will have now approximately 45 minutes, 50 minutes to share with us. Then afterwards we'll have some Q&As if you have any. If you want to ask anything during, then please use the chat, like the chat box, the reply to all chat box in the GoToMeeting. Yep. And I think that's it. Keep yourself muted during the presentations. That's all I want to ask. But
okay. Thank you very much.
Good luck.
Yeah. So thank you, Renske, and we will be having sort of quite technical presentation today. This is based on actually something that I have been teaching future engineers with, and I have a disclaimer as well that we're not going to all of the details. There might be some solutions on the markets that I'm not mentioning, some very novel solutions, but this is supposed to be the basics of what's actually the technology, where does the technology come from, which the robotic vehicles are using, and basically to see the idea of how and what's the basis of robotic shuttles, robotic vehicles, how they operate. And for that reason, we are starting actually with a short physics lesson, so to speak. So we're going to go to the actual physics of signal processing and seeing. And I hope that this is not too overwhelming for you. I'm trying to keep it sort of understandable, but yeah. So if we delve in, the first thing we have to see is also what kind of hardware I'm talking about. There's a lot of more hardware where it comes from, and of course there's the software. But first of all, we have this sort of setting. So we have the vehicle technology, which we will not be talking today too much. that's kind of old news. It's basic electric vehicle technology. And then we have the sensor technologies, the sensor banks, and that's something that we will be talking today. And the topics are basically LiDARs, sonars, radars, cameras, accelerometers, and radio wave communication systems or radio systems. So this is kind of the agenda for the day. But to understand what we're talking about, I will go through some basic physics and technology. So where we are playing is the electromagnetic spectrum. So the spectrum is, it tells us how photons actually work, how radio waves are passed. And here you can see in the picture that we have a lot of different sort of categorizations for the radio waves, and the radio waves we can, as humans, we can sense is only a really small portion of it. It's the visible spectrum, and we see it as a light. But there, on the spectrum, there's everything from electricity to cosmic rays, to X-rays, gamma rays, and that sort of stuff. And we're using some part of it in the sensing technology of the robot buses. You can see the LiDARs are using mostly visible, or well, below visible spectrum infrared radiation, and then radars are usually on the microwave, radio wave area. So those two areas are the main areas that we are using in the sensing technology that is based on photons. And there are a lot of characteristics that comes with the wavelength of the radio waves, and this is what we are going to go to next. You can see in the below that there's this two arrows. When the wavelength is getting shorter, we increase energy, and that is why, for example, the X-rays or gamma rays are so dangerous to humans. They're so high energetic particles that they can actually physically knock off like building blocks of DNA, and that's why and that can cause cancer, and that's why we are avoiding high energy particles. And in sensing technology, we need to take also these kind of also these kind of safety issues with us. So we're using radars and LiDARs, and just some basic principles and concepts of signal processing. So what we're talking about are basically frequency, and the frequency is measured in hertz, abbreviated Hz, and it means basically how many times some event is recorded in some time period. And when we're talking about signals, it means how many times the peak energy of the signal is recorded in some given time unit. And you can see basically in the graph that when you're plotting this energy level in time graph, so energy is up and down and time is right and left, you will see that the wavelength is from 0 to 0 or peak to peak. And with that frequency also comes wavelength, and the wavelength means the distance between two peaks, so level of reference or reference to reference level, which is the 0 level over there. You can see in the animation that there's this sine wave signal which is making peaks and valleys, and you're measuring basically the amplitude, which is the height of the curve, and also the wavelength of the curve, which is the density of those peaks. And there's also something called modulation. You probably heard it in the radio. There are two often known modulation types. There's amplitude modulation called AM, and the frequency modulation called FM. And that is for carrying information. It means actually the modulation means we modulate some signal with another signal to get some information carried over those signals. And you can see quite well in the animation what it means. Amplitude modulation actually increases and decreases the amplitude, and frequency modulation increases and decreases the frequency. So in the animation, it's quite visible. And then there's a third or fourth big thing is phase and phase shift, which means kind of if you have two similar signals, how they are positioned in relation to each other in the graph. This is a lot to get in. You know, I know that if you're not familiar with signal processing, there's a lot of concepts now, but I hope that you have some idea now that we're talking about frequency, wavelength, amplitude, and phase quite often, and modulation in some cases. And all of these are related via basic physics. You can see the equation there. The wavelength is noted by this Greek letter lambda, and lambda or wavelength is the velocity over frequency, so it comes from there. Some basic physics. I hope you're still with me. Do we have any people dropping out already? So where we get with this, where we get with the wavelengths is that we can take signals, we can take basically photon radiation, and then categorize it with with these concepts that we were going through. So here I have a list or table of different classes of radiation, basically, and you can see that they are categorized by frequency, wavelength, and energy, which we're not going in this lecture. And you can see that the radars are operating in wavelengths starting from 1 millimeter to 100 meter, and the lidars are operating from 0.25 micrometers to about 1.6 micrometers. This might change. There might be some solutions on the market that have different, but this is kind of the usual range. And we're operating with light, so we're using the speed of light in the equations denoted as c. So these work with photons. Even if we're talking about radars, the particle that we're talking about is photon, which is basically the light particle, but you cannot see it in the radar frequencies. So just to recap, when the wavelength increases, when there's higher wavelength, the frequency gets lower. The resolution gets larger, and I will get back to this resolution thing. The antenna size grows. So this is the first real physical, tangible thing that you will see. That when the wavelength is increasing, when we have bigger, for example, if we have a radar that has wavelength of 100 meters, if we have the medium frequency or high frequency radar, then we have to have a huge antenna to actually create this wavelength. And their energy gets lower. So when we get to the lower frequencies of radars, we get less energy. And this is what I said about the X-rays and those. They have really short wavelength and high frequencies. When the frequency increases, it's kind of the opposite. So wavelength gets shorter, antenna size gets smaller, resolution gets smaller, and the energy increases. So between lidars and radars, you can see that lidars have smaller resolution, smaller antennas. And then why are we not using only something? Why are we not using only lidars? Why are we not using only radars? We have different media. So in this case, media being like air or another car in front of us. They have different sort of absorption spectrum or spectra, which means that with different frequencies, the air is blocking the radar frequencies in different ways. I will have a picture of that later on, but this means we need to select our wavelength of the solution of the sensor to actually penetrate through what we're trying to see. So it's almost often some sort of compromise in the solution that we're using. And the resolution in this purpose means the minimum size of the detectable object. This is not very scientifically rigorous term. It's something I like to use. Resolution in sensor technology might mean other things as well, so don't. But in this case, we're talking about when the resolution is small, we see small objects. Basically, that's the idea. So this is about atmosphere absorption spectrum. The thing here is that you can see that in atmosphere, in air that we're living in, the light can penetrate quite well, and some radio waves can penetrate quite well, but for example, gamma rays, X-rays, and ultraviolet light is blocked 100% off, and also long wavelength radio waves are blocked. So this is something that you can see happens, and this is why we are using what we're using. This is why we're using visible light. This is why we're using radio telescopes for astronomy and that sort of stuff. And that's also why we have satellite telescopes. So to operate in different wavelengths, we have to send them out from the atmosphere. Yeah, something more. Oh, this is about the reflection. So basically, reflection is the thing that we're playing with. When we have sensors like lidars and radars, we call them active sensors in some cases. They send a signal of some sort, and they send a signal in the form of package of photons, basically. And then they get it back reflected from something that we're trying to measure, be it a car or a wall or a human being. We also have passive sensors, such as cameras or our eyes, that they just reflect, measure something that's reflected, and the actual photons are emitted by something else. So basically, we see that sunlight is reflected from some objects, and that's how our eyes function. And from the reflection of these sensors, basically, we can measure at least the time of flight. So we can measure how long it takes for the photon to actually leave the sensor and then reflect back. Oops, there's some finish there, sorry. It's easy to measure with a pulsed signal. So when we're sending signals in pulses, so click, 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 it means that it's easier to measure when those pulses are coming back. But if we're sending continuous wave sort of system, so all the time the same, we need some kind of reference to use measuring this measure of distance, and that's what we're doing later on. And then what we can also do is we can measure Doppler effect, or also known as phase shift. So this is the Doppler effect is quite often used or explained as if you hear ambulance driving past you, you hear that the pitch of the voice or the sound of the ambulance sirens is changing. And this is Doppler effect. It means it's sort of phase shift in action. And this is something you can also measure from the signal properties, how the signal is reflected and what kind of changes there are in the signal properties. In the frequency, is it getting more frequent or less frequent, or has the wavelength changed? And this is something that we can use to measure object velocity. So this is something that's used in Doppler radars, for example. If the police wants to use their pistol radar, they use the Doppler effect. And also in some radar signals, we can measure the frequency. So we modulate the frequency so that at one point we send higher frequency, and one point we send lower frequencies, and then we send this continuous wave, and we see the reference level when it bounces back. And this enables like radar-based distance measuring. And yeah, so we have different things that we can measure with these sensors in reality. Yeah. So if we get to the actual technology itself, I hope that we have now sort of understood that there are different properties to different signals, and we can measure those properties to our advantage. And the first one I want to use is, or talk about, is the LiDARs. And the LiDARs are very, very important in automated mobility. And they are, the LiDAR name comes from light plus radar, or light detection and ranging. It's the same thing. There's some etymological history behind it. But it's like light-based radar. And what it does is it sends photons, usually in the UV light, and measures the reflection from objects. And it measures the time of flight, and in some discrete systems, it measures also the phase shift. And these points of light that are reflected, we know that where in the space, where they are reflected from. We can use that data to create a point cloud. So basically you send one photon and it bounces back from somewhere, and you send another one to a different location, and then you see where those, how far from your LiDAR those are, and you see where they are. And then you map out those via computer to create a point cloud. Basically you have a cloud of points in the space where those reflections have been happening. And when you do this enough times, you can actually map out the environment and see objects. So the wavelengths typically are in the ultraviolet range, and this is why I want to talk about this, is that quite often if you're going into like shop or buy a LiDAR, you can see the wavelength stated there. And the thing is that different wavelengths of lasers, these are UV lasers basically, they have different sort of properties when it comes to penetrating air, penetrating fog, mist, snow, that kind of stuff. And also the energy levels that you can use when it's safe for eyes. So we need to use those kind of energy levels that they are safe for human eyes, because we don't want to make people blind when they're walking down the streets and there's robot buses. So also this energy level, and I'm now talking actually the pulse, sort of, there's two different energy levels, but I'm talking about the watts that's used, not the actual signal energy. It's a bit complicated, but the thing is that we can, changing this wavelength, we can have different sort of properties, and in some cases we might have two different kinds of LiDARs working together so that they see different things. And the small wavelength actually makes it possible to detect very small details. So we can detect with LiDARs, we can detect basically like fog, or because it's reflected back from very small molecules or particles, and it also, the thing is that it creates quickly a huge amount of data. So we have a lot of data coming in, especially if we have multiple LiDARs, and this needs quite a bit of computing power. And usually in robot buses, some of the computing is done real time inside the vehicle, usually the obstacle detection, and the mapping out of the area is done. Well, the map is created from data that is recorded. So but computing data is something, computing power is something you need usually quite a bit with LiDARs, and it depends on the resolution and on the size of the area you're mapping out. And we have also several kind of LiDARs. We have multi-layer LiDARs that can be used to create 3D maps. So they map out X, Y, and Z, so height and length and width, basically three coordinates. And you can create very physical maps, 3D maps with the multi-layer LiDARs. And with a single layer LiDAR, you can only produce two-dimensional sets. So you can only see like a flattened image seen from basically above. In the picture here, I have Velodyne VLP16. It's a 16-level LiDAR operating at 905 nanometer wavelength, so kind of in between the range. This is something. This VLP16 is something that you will find in most of the current robot buses. So it's like the workhorse of LiDARs these days, and it's created to use to 3D map systems. And what I've understood so far, it's the cost and performance is good value for money. And the LiDARs, they have hundreds of applications outside of robotic vehicle, robotic movement. LiDARs are used really much in construction and especially in geographical surveys, mapping out forests and land areas and that sort of stuff. So LiDARs are used, and they now, recently, there are a lot of companies that are developing LiDARs, and the prices have come down quite a bit. So they are getting cheaper and cheaper all the time. LiDARs have been very expensive in the past. Here you can see actually a 3D point cloud map of a railroad bridge and the surrounding area. The colors actually those are something that the algorithm is adding later. So basically, LiDARs don't have color information. There could be some sort of system that actually has color information, but usually there is none. So this coloring is done afterwards. But as you can see, the detail is very fine. So you can see all the structures in the bridge. Some LiDAR components. We have a rotating or sweeping mirror in the scanner, and the scanner is actually sort of scanning the environment, sending the pulses and measuring the pulses, and they measure the exit angle of the photons, single photons, very precisely, so they know where they're sending it, where it's sending those pulses, and the mirror is receiving the reflected pulse. One of the most crucial components is the clock, and the clock actually measures the time of flight. So there's a very quite precise clock in the system. And then also sometimes, especially in the geographical survey, they have localization methods built into the sensor. But sometimes these sensors can be external, or we can use external data. Like in robot buses, usually we have different or external localization sensors. But in some cases, it's really good to know where you are, where the sensor are, and usually there's some sort of localization sensor in the LiDAR itself, so it knows where and in what position and orientation and angle it is. Because these are very often used in robot buses, I took one picture of EZ10 robot bus from EasyMile, and basically simply an electric vehicle or which is automated can be quite simply a vehicle with single layer LiDARs in the corners, so it creates a 360 degrees of this cage, safety cage in one level, and then localization LiDARs are usually located in the roof, and those are usually multi-layer, so you can create a better map. This is like the basic setup that's often used. It's not like, not everybody does it like this, but it's kind of what it can be. And also for enhanced object detection, if you put a multi-layer LiDAR on front and back, you get more detection for the obstacles. So some pluses and minuses for the LiDARs. They are very accurate and very detail rich, and we have, as I said, we have different frequencies, and those are suitable for large scale of solutions, from surveys to automated mobility, and they're effective for large scale mapping. There's actually a comparison of two different sensors, high resolution radar and LiDAR. LiDARs are quite expensive, and they are getting cheaper. They need a lot of computation power, and this is thing that we also have in in the robot buses that they issue false positives. So when we have dust or leaves, if there's no algorithm that's filtering those out, then we get a false positive reading because it's such accurate detail. And in some cases, non-reflective surfaces can be a problem. If we go to radars, radars are, the name comes from radio detection and ranging. They are measuring sensor based on radio waves, not light, but radio waves emitted by photon. And usually active radars, they have their own radio wave transmitter, and passive radars have external transmitters. And the wavelength, we saw that there's a lot of room in the wavelength area, and it needs to be selected by the need and the solution. And if we are going over 3 gigahertz of frequencies, the environment, the composition of air affects the radar performance quite much. First radars were created in the beginning of last century by Hulsmeyer, and they were this spark gap type of radars used to detect ships. And during the World War II, as we all know, the radars experienced a lot of development, especially in the UK and United States. So these are the frequency designations, and there's a lot of bands. And some of you might have heard of VHF. It's used for radio communications as well, and UHF as well. But the thing we are interested in is basically the W band, which is used for autonomous vehicles. And it's between 75 and 110 gigahertz. Also, now I have to mention that some of the companies that are creating autonomous vehicles are using ground-penetrating radars, so these VHF area radars for localization. So they're actually using seeing underground and seeing the underground structures and using that for localization, but it's not used for obstacle detection. So we're using in the autonomous vehicles, we're quite in the higher frequency range. And as I said, when we go over 3 gigahertz, the environment is affecting quite much on the performance and penetration of the medium. So this is how what we're using these days. Those are used often in the ADAS, so Advanced Driving Assistance Systems, such as automatic emergency braking systems, AEBS, and automatic cruise controls. And previously, those were in the 24 gigahertz range, but now usually they are in the 77 gigahertz range. And because they have a high frequency, it means that the 77 gigahertz band, they have a small antenna, which is easier to fit into the vehicles. And these are used in passenger cars quite often as well. And also, since they are absorbed, this wave of radar doesn't pass through air so well, it means that there is much less cross interference. So if you have a lot of systems that are working on the same wavelength, they can actually interfere with each other. But if you have a lot of dampening or a lot of absorption from the air, you don't have that problem so much because they don't travel so far. So this is also why using this high frequency band is quite okay. Yeah, so radars are quite affordable, and we have a lot of frequency range that's actually giving a lot of design freedom. And apart from these synthetic aperture radars, or SARs, they are not very computationally heavy. The problem is that the resolution, as we saw, is not as good as in LiDARs, so it's might not be enough for automated mobility use by itself. And usually these do not function as the only sensor for robotic vehicles. Also, we have the laws of physics. So they dictate the antenna size, and if we would for some reason want to use like 3 meters wavelength of 3 meters long, we need fairly large antennas. So that's why we need to stick to the higher frequencies. Also, tracking moving objects reliably, especially if they're decelerating, that can be difficult to do some reflection physics. And also the interference, we're operating in the wavelength area where there might be some other solutions, other devices, so we need to see the interference and take the interference into consideration. And also there has been some issues where a large reflecting surface, like a big metal plate, it might flood the receiver, so it doesn't see anything besides the reflection from the large surface. And also conducting materials can be misinterpreted, or they can be seen wrong if there's like a metal railing or something like that. But this can also be used as an advantage. So if you want to create a cage or something for a radar operating vehicle, then you can build it out of different sort of materials, conducting materials, and you will know that the vehicle will see it differently. So this is both an advantage and a misadvantage. And also, as I said, radars do not carry color information, so you cannot, for example, see what color of traffic light you're having with the radar. Moving on to sonars, which are a bit different than what we have been talking right now, but they are quite important sensor in the autonomous mobility. And sonar comes from sound navigation and ranging, and this is sound wave-based sensoring. So please note that these are sonic vibrations, so these are vibrations of air and not vibrations of photons. So this is not electromagnetic radiation. This is compression and decompression of air. So it's a bit different. When we're talking about frequencies, we're talking about the frequencies on which the medium or the air or the metal or whatever is compressing and decompressing. Usually humans hear about from 20 hertz to 20 kilohertz, so 20,000 hertz. That's like the hearing range of perfect hearing, and sonars can operate from in that area, or usually they are not in the audible area, so they are infrasound below the 20 hertz or ultrasound over the 20 kilohertz, even to the gigahertz range. So that's why you don't hear a whining pitch of like a parking sensor of your car, apart from the beeper. Also, sonars are also made by the evolution, so they're made in nature, used by very many animals. For example, bats. The echolocation of bats is sort of sonar in nature. Also, some marine mammals and insects are using sonars. So it's very old, so to speak. And humans have been using sonar, sort of wave-based ranging from the 14th century, 15th century. So it's quite old technology, although these days it's of course a bit different. So how sonars work? They send a sound pulse or a ping and reflect that sound coming back. So it's known as an echo, and that's where the echolocation word comes from. And when we compare the speed of the sound in that medium that we're using to the duration of the reflection, the distance can be calculated. But one thing to notice here is that the speed of light, the speed of photon in vacuum is 300,000 kilometers per second, so very, very fast. The speed of sound in seawater is 1533 meters per second, so it's much, much, much less. So the pulse is very much slower in sonars than in radars and lidars. We can use multiple sonar sensors, and so we can have the direction of the reflection. So this is sort of one reason why you have in the parking sensors of your car, you have a lot of those round things. So you can actually deduce the direction where the reflection comes from, and also see a bit better. And in some cases, the frequency shift, so basically the Doppler effect is also can be measured in in some sonar systems, and it gives better results. It gives a more accurate picture of what's the object. And sonars are quite affordable, so they are. That's the reason why they are used in fishing, boats, and in automotive sectors. They're used in parking sensors. Computationally, they're quite light. They don't need a lot of computing power, and they're a good addition to the sensor fusion. So whenever you have some system that has sensors, sonars are quite good addition. There are some drawbacks, of course. Smooth surfaces. If it's just plain smooth surface, it can be detected wrongly. It might be also transparent in some cases, especially if the observer or the car or something is moving. But this can be mitigated by clever technology. Also, one object can create ghost echoes, so it can vary the reflection. And due to the medium, if we're using air as a medium, for example, differences in temperature and pressure and that sort of stuff, and other factors might affect so that the flight of time, so the distance, the time of the pulse reflecting back might vary, so that might cause some weird readings. And usually, as I said, this doesn't work as an only sensor for robotic vehicles. And the signal is very slow compared to photons, so you need to take that into consideration as well. Then we go quickly through the stereo cameras, because these are quite easy. We have visible light cameras and infrared cameras, and infrared is also, there are different sorts of infrared based on the wavelength and the frequency. And what we are interested in are actually the night vision, so the near infrared and then the long wave infrared for passive thermal imaging. So what we can see in the near infrared is infrared radiation reflected from objects, and then in passive thermal imaging we can see objects like human beings or animals or basically anything. When they emit themselves thermal heat, it can be viewed with this passive thermal imaging. And in the future there might be some sort of terahertz imaging, and in the far infrared area there's also these motion detectors using that. So the far infrared in some cases can be interesting, but it's not very often used in the automotive sector right now. But the passive thermal imaging is basically like, these are like two ways of night vision, if you've seen in some movies or something. And the night vision equipment is sort of the green tint of a camera, or yeah. So that's and those are quite often used in very many areas. And cameras are very affordable, so they're cheap, very cheap, and very good for the money. They're easy to use because they're analogous to our eyes, apart from the infrared cameras, but basically it works in the same way. And they're a significant addition to sensor fusion. And with proper algorithms, some people are saying that cameras could be paired with radars and used as the only sensors for automated vehicles without LiDARs. I'm a bit skeptical of that, but the future will tell us. And also, we can see in low light environment or even in no light environment with the passive thermal imaging. So these are really interesting scenarios for some specific solutions. And also in the visible light range, cameras retain color information, so you can actually, for example, see the traffic light. The penetration of signal is weak. We cannot see through non-transparent objects, and that's sort of a problem in some cases. And at least not now, they are not the only sensor that's working. And then there are these machine vision algorithms that are needed to reach the full potential of stereo cameras. And also sensors are quite easily flooded. So bright sunlight, we have a lot of sunlight. Reflection of bright sunlight can totally block all the visibility of the camera. So let's go through these. These were actually the sensors that are seeing the environments. So now we'll move quickly through some sensors that are knowing where the vehicle is itself. You can do that also with the LiDARs, but these are additional. So accelerometers, so inertial measurement units, or IMUs, are often used in automotive solutions and in robotic vehicles. And what they do is that they're these very fine, high-precision microelectronic devices that actually they measure the angle, yaw and pitch and roll and acceleration of the vehicle in all three axes and rotational axis. So what they do, they see how the vehicle move from within inside the vehicle, basically. And we can use this for many solutions. We can use this for portraying acceleration information to various systems, to safety systems, and even convenience systems. But we can also use this to approximate the location where this vehicle is. So this is old method. It's from naval navigation called as dead reckoning. So we can take known position. We can take a position that we know, and then we can measure how long a distance we have moved in what time with the inertial measurement, and then we know actually the new position as well. I hope you understand. So, but these IMUs can be used for rough calculations. The problem is that they are very subject to cumulative errors. So over long periods of time, you will get a large error. But these are used very widely in anywhere in high tech, including cell phones. If you're dropping your cell phone, it knows with an accelerometer that it's being dropped. And computers everywhere. And also, for example, the airbags of your car they are launched from the data of an accelerometer. So there are probably tens of IMUs or accelerometers in any vehicle that's on the road these days. But these are really high precision, very fine objects, and also quite expensive. So the last thing here, I think I've been talking almost my time full, but the last thing is radio communication, because this is in the heart of smart mobility, and the vehicles will be connected to each other. We talk about V2V, vehicle to vehicle, to the surroundings, vehicle to infrastructure, or V2I, cloud services, V2C, vehicle to cloud, and everything else you can actually imagine. So we're talking about V2X, vehicle to everything, because people were probably bored of coming up with new V2 something. Usually this connectivity is based on radio communication. And the main role is in the cell phone networks that we have these days. We're using standards like 3G, 4G, 5G in the future, and also Wi-Fi frequencies. ITS G5 is basically a Wi-Fi standard. So these are the new things that's coming up. I say usually based on radio communication. In theory, and in some solutions, infrared light can be used also to communicate with, and it's actually used these days to communicate with the infrastructure or other vehicles. But quite often it's also radio communication, or mainly. And when we get to low latency links like 5G, we can have more video feed, and it helps with the remote operation, maybe even teleoperation where you're driving the vehicle remotely. But that's something that the future is holding. And when we get 5G, I think we get new services of robotic movement. I say that 5G, some people say that 5G is needed for automated vehicles. For them to happen, it's a bit debatable if it's actually needed, if we can operate with other systems as well. And the 3G is quite often used, for example, to transmit like location data, where the vehicle is, and correction data for the global positioning systems. So quickly through the global positioning systems, we have A lot of satellite navigation systems, they are called the GNSS as a catchphrase, Global Navigation Satellite System, and we have the American GPS, the EU Galileo, the Russian GLONASS, and then we have the Chinese Compass or Baidu, and also Japanese are thinking of their own. And they operate in the UHF band quite often, so in the same bands as some, for example, some radars. The global positioning is actually used quite often for the vehicles to position themselves. So it's very important that we know where the vehicles are in the world, in the space, in the map, in the reference map, and global positioning system is one way of using that. And that localization is also usually enhanced with localization lidars, which actually use the surroundings and refer that to the baseline map, which is recorded beforehand, and then they see basically where they are. But I think we're going more and more to the global positioning way of localization. And because satellite data is not very, there's some errors in the satellite data due to very many things. We also use a thing called differential GPS or DGPS, and it's an error-corrected localization, and it gets the correction data over the internet. So we have some bases on ground that are fixed, and they know where they are, and those are used to correct the data that's coming from the satellite. Yeah. Quickly, from the satellite navigation system works with satellites on the sky, and the receiver needs to see at least 4 satellites in order to find coordinates, usually more. And the more satellites you get, more satellites you see, the better the localization is. There's a lot of physics going on here, and it's quite interesting, but maybe we skip that now. But just to summarize, the robotic vehicles, they rely on many different solutions, and the data is provided by high-tech sensors, so we have a lot of sensors. And the key actually is to have better sensors, but also better data processing, better software algorithms to actually make use of that data. And that's in the heart of the sensor fusion, that we get data from different sorts of sensors, and then we use algorithms to get the best situational awareness from those sensors, and then we can operate better than humans. So humans have only eyes, hearing, and sense of acceleration to guide us, and then we have our brains to use that data. And we try to make the robotic vehicles better than the actual humans. And sensor fusion is still quite data heavy and also very expensive for the day. But it's something that I think if we want for the robotic vehicles to operate in any conditions and in the infrastructure that we have now, we definitely need sensor fusion and very good algorithms to operate safely and efficiently. That is basically my time, I think.
Thank you very much.
Yeah, it was a bit over 45 minutes, but
yeah,
I
no
hope
problem.
people are still
Thanks
awake.
a lot. Yes, you didn't lose anyone.
Yay!
So that's at least not from the list of attendees. I don't have any questions in the chat box, but if anyone wants to ask something, then please do, or turn on your mic. I was wondering, maybe you can say a little bit, all these different types of sensors, are all of those used in all the robot buses? No. Or does each robot bus manufacturer use a different set of sensors, and that's how they distinguish themselves? Yes.
That's a very good question, because there's quite some of the robot buses or the shuttles are quite simple. So basically everybody that I've seen have at least one LiDAR and an accelerometer or IMU and the GPS. So those are the 3 that's found basically in every vehicle. But a lot of vehicles, and basically cameras are usually fitted in every vehicle, but they're not quite often used. But you get a set of sensors, as you can see that we have a lot of possibilities, and then you see the solution, and the manufacturers see the price and the solution where it is used, basically in what environment and that sort of stuff, and then they choose the combination based on that. But so far, what we've seen is that nobody has had the best, like the optimal or the solution that works everywhere so far. There are some that are very close, but the most simple ones are still quite simple ones. But yes, definitely there are not all of the sensors in all of the vehicles.
Mm-hmm.
Yeah.
But you would say the more the better.
Basically, that's my physics-wise, it's that. But when you go to actual reality and like budget
And business models.
Yeah, business models,
Yeah.
yes,
Yeah.
and that's reality.
Mm.
Yeah. So, and about the price we were discussing earlier is that quite often, for example, when in 2015, 2014, when these shuttles were coming, the price of the sensors were quite significant amount of the price of the vehicle. Especially the lidars have been very expensive, but they have now the prices are now, I think, half or quarter from like 5 years ago. So yeah, but it depends. Yeah. Okay.
All right, thank you.
Yeah.
Well, if there are no questions from the audience, no? Good.
Good.
Then
Nobody understood anything.
no, I think you were very clear. So thanks very much. We'll wrap this up. This video will be edited and put on YouTube.
Next autumn, I think we have all the 3 videos.
After the summer, yeah. Yes, so there will be more information through the Fabulous social media and website once that's done in a month and a half or so. And and as I said, the next webinar will be on the 3rd of September on cybersecurity. So warmly welcome to sign up for that as well. I'm not 100% sure if the registration link is already active through the website, but we'll notify everyone once it's up. So
Very good. Thank you, Renske.
thank you very much. Okay, see you next time.
Bye-bye.
Bye.